In my previous videos, you've learned how 8 valence electrons, or rather noble gas structure, is particularly stable for an atom. In this video, you'll learn how this affects the properties of the alkali metals and the halogens. So, let's start with the alkali metals, which we find here to the far left of the periodic table. Well, yeah, hydrogen isn't exactly a metal, except at very low temperatures and extremely high pressure, but otherwise they are lithium, sodium, potassium, rubidium, cesium, and francium. And I actually imagine that you should learn them all in order to. So take this to your notes. We have hydrogen with the chemical symbol H, then lithium Li, sodium Na, potassium K, rubidium Rb, cesium Cs, and francium Fr. The alkali metals have in common that they only have one single valence electron. Let's, for example, look at the electron configuration for lithium to see that. Lithium's atomic number is 3, which means that it has 3 protons in its nucleus. Thus, it also has 3 electrons to be distributed in the different shells, and as usual, we start with the innermost shell. 2 electrons in the K shell, which then is full. The last electron ends up in the L shell, like this. Since the alkali metals only have one valence electron, they are very reactive. When an alkali metal reacts, it is oxidized, it only has to lose its single valence electron to get noble gas structure. We'll study carefully what happens. Now, I draw a nucleus like this with 11 protons. Then there are also 11 electrons to distribute, and as always, we put 2 of them in the K shell. Then we place another 8 in the L shell, which then is full. 2 plus 8 equals 10, which means we only have 1 electron left to distribute, and it ends up in the M shell. So what kind of an atom is this? Well, if we check our periodic table, we see that the atom with atomic number 11 is sodium, right there. So let's write this below our drawing here too. Now, when the sodium atom reacts with something, it quite easily gives off its valence electron. The sodium atom is oxidized. To remove an electron, we must add energy to it, just like if you want to lift a rock from the ground. The energy required to completely remove an electron from an atom is called that atom's ionization energy. So, we write here that we add some energy to remove the electron. But what is then formed? Let's draw the nucleus again here with its 11 protons. There are still 2 electrons in the K shell and 8 in the L shell. But 1 electron has been removed, so we write it here instead. Now please note, first let's count the protons and electrons that are left. There are still 11 positive charges in the nucleus, but only 2 plus 8 equals 10 electrons left. 11 positive charges and 10 negative charges, this means that there's a surplus of 1 positive charge in the ion that now has formed. This ion is called a sodium ion. We write it Na+, which means that it has a single positive charge. In the chemical equation, we also add an electron here. You must also note that the sodium ion that is formed now has 8 electrons in its valence shell. Yeah, the M shell no longer exists, so the L shell becomes the outermost shell, and it contains 8 electrons. And that is, as I said earlier, particularly stable. Also note that since the sodium ion only has 2 electron shells, whereas the sodium atom has 3, the sodium ion is considerably smaller than the sodium atom. What's happened right now is that the sodium atom has been ionized. In this case, it means that it has been oxidized to form a sodium ion. All the alkali metals are reactive, but which one is the most reactive? Well, the further away a valence electron is from the nucleus, the less it feels the attraction from the nuclear charge, and the easier it is given off. This means that the further away the valence electron is from the nucleus, the less energy is required to ionize the atom. In other words, the lower becomes the ionization energy. In francium, down here, the valence electron is in the 7th electron shell. This means that it is very easily given off and that francium is extremely reactive. In lithium, the the valence electron is in the second shell, which makes it a little bit more difficult to oxidize. Thus, lithium is not at all as reactive as francium. This leads us to the conclusion that the reactivity increases as we move downwards in group 1. When an atom is oxidized, it almost always gives its electrons to another atom, which is reduced. A classic experiment is when solid sodium and chlorine gas react. Then sodium chloride forms, and quite a lot of energy is released in the form of both light and heat. Chlorine, that's one of the halogens, so now the time has come for examining those two. We find them here at the right of the periodic table in group 17. Here, I have also written that halogens means salt producers, because this is precisely what forms when they react with a metal, like, for example, sodium. I also want you to learn all the halogens by heart. The most important halogens are fluorine, chlorine, bromine, and iodine. There are only a few grams of astatine in the entire Earth, and tennessine is completely synthetic, which means that only a handful of atoms have been made so far. So those two halogens are not as important as the other ones, although they still are interesting. What's common for all the halogens is that they have 7 valence electrons. This time we exemplify by looking at the electron configuration for fluorine. Fluorine has the atomic number 9, and thus also 9 protons in its nucleus. There are 9 electrons also to distribute on the different shells, so we put 2 of them in the K shell and the remaining 7 in the L shell. Having 7 valence electrons make the halogens very reactive and consequently very poisonous. They only need to gain a single electron to be reduced, and then they get 8 valence electrons. They get noble gas structure, which, as I said earlier, is particularly stable. Let's have a look at chlorine, which I happen to know has the atomic number 17, and thus also 17 protons in its nucleus. We put 2 electrons in the K shell, and then 1, 2, 3, 4, 5, 6, 7, and 8 electrons in the N shell. That makes 10 electrons so far, and we put the remaining 7 in the M shell. 11, 12, 13, 14, 15, 16, and 17. Now let's see what happens if we add an electron to this atom. And down here we also write Cl plus E minus. We still have 17 protons in the nucleus, 2 electrons in the K shell, and 8 electrons in the L shell. But check this out, we now have 8 electrons in the M shell as well. This means that we now have 17 positive charges and 18 negative charges. In total, the chloride ion that now has formed has a surplus of 1 negative charge. We write the chloride ion Cl- since it has 1 negative charge. Also, when we add an electron like this, the electron will lose energy. That energy is released, which we add to the reaction like this. It's this released energy that is given off in the form of light and heat when sodium and chlorine react. Now, what about the reactivity of the halogens? Well, the closer to the nucleus the valence electrons are, the more they feel the attraction from the nuclear charge. This means that the closer the valence electrons are to the nucleus, the easier it is for the atom to gain an additional electron. This also means that the closer the valence electrons are to the nucleus, the more energy is released when an electron is taken up. In fluorine, the valence electrons are in the second electron shell, which means that the fluorine atom very easily takes up an additional electron. In iodine, the valence electrons are instead in the fifth shell, which means that the iodine atom doesn't take up an additional electron quite as easily. And what it looks like in astatine and tennessine, we really don't know since there's too little of it to perform any experiments, but they surely are even less reactive. The conclusion then is that the reactivity increases as we move upwards in the halogen group, like this. So, now that you've learned about the alkali metals and the halogens, don't forget that you can learn even more and check your learning on my homepage. Links are in the description.